Good evening. I'm Benetti, student leader, Year 11 Year Council Chairman, Senate member for 12RG, former ICT subject prize winner, current ICT subject prize winner, former Vince Trophy winner, an all-round nice person. I'm also a pupil at Archbishop Hallgate School, a Church of England Academy, leading edge science college, healthy school, Ellen MacArthur Pathfinder School, and home to the world-famous Spiritual Garden. This is the second video I've made for Decision 1 Further Mathematics.
I'm going to be talking you through Kruskal's algorithm. So what I want to do is create the minimum spanning tree. So first you've got to select the shortest route, which is e to d, which is 4. So I'm going to draw that on my little diagram down here and label that with 4. With Kruskal's it does not need to be connected the whole way through, so you can connect the next shortest one. However, I'm going to choose the one that is actually connected, which is the value of 5, which is e to a. The next one to select is the other one of 5, b to c. The next shortest is one of these two. However, you wouldn't pick a to d because you don't want any loops in this minimum spanning tree. So you would select the value of 6 from d to b. And there is your minimum spanning tree. I'm Sam Rippon. I'm 17. Bye-bye.
I'm going to be explaining Prim's algorithm. So we choose any of our vertexes. So we're going to start from B and we choose the smallest arc from B. So that's 5. So there we go. 5. And then we choose the shortest one that comes off of the two either side of that, which is 6 here. Then we pick that one. And then now we've got to choose the shortest one from any of these points. And that's this 4 here. And then we choose the shortest one from any of these vertices, which is E down to A, which is 5. And now we have the minimum spanning tree.
We do.
It is possible, and sometimes useful, to describe graphs such as this in tables, where the table shows every possible combination of vertices. For example, E to C, we could mark in this table as being no connection by just putting a dashed line. And then A to B, we would mark on with the value 7, since that's the weight. So I'm just going to complete this table.
Are the E and the I the right way around and weird, or is it the other way? Is it IE or EI?
So I'm now finished, and I can apply Prim's algorithm to this table. Let's say I want to start at vertex A. The way I can do this is I can cross out the line from here for A, and then highlight A up here. You don't have to do this, but it is helpful. And then I find the lowest weight coming from A. In this case, it's 5. Now, the reason I'm crossing all of these out is to avoid creating cycles. Cross the rest of this out, and I can write AE on my graph. So now I've got E as well to pick from. The lowest one here is 6, the lowest one here is 4, so I'll select that because that's the lowest overall. And so I've now added ED, which has a weight of 4. Now I can look at D as well, so the lowest here, well there's no other connections for E. D, the lowest is 6, and A, the lowest is 7, so we'll go with the 6 here. Cross out all of B. Now B has been added, and we can add DB. Now if we look at B, 5 and 8, so 5 from B to C, we'll add in BC, and this is our new tree of the lowest
Ben, 4
weight.
PM. This is Dijkstra's algorithm for finding the shortest route from the start to the finish of a network. First of all, you label your first vertice where you want to start, usually labelled S, with a 1, because that is the first vertice you are using. It has a final total value of 0 because it takes you 0 kilometres to get there. From here, you input 4 to D and 5 to A as working values from S. You then see which is the shortest and make that your second point. From your second point, you then do the same as you did from the start. So you would go from D to F, which would be a total of 12. From D to B, which would be a total of 10. From D back to A, but that's larger than 5, so you don't write it down. And then once you've done that, you look for your next highest vertice, which in this case is A, so it would be vertice 3 with a weight of 5. And you then do the same again. 3 in there would be 12, which is greater than 10. You wouldn't go back to D because you've already put that as a final value. Looking B is the next vertice, 4 and 10, and then 15. No, that's more. So your quickest route is S to D to F, length 12, and that is Dijkstra.
So now we're going to do the route inspection algorithm. When you're doing the route inspection algorithm, you want to write down the degree of all the vertices first. We have A, which has 1, 2, 3. B, which also has
3. C has 2. D has 4.
E also has 2. Right, so now we've written out all the degrees of our vertices, we can now see that there are 2 vertices with odd degree. That's A and B, meaning this graph is non-traversable. To make sure that you can visit every single vertex once, you need to have a traversable graph. So to do that, you would simply add in the shortest arc between the 2 odd vertices. And in this case, that happens to be the arc directly linking A and B, which has a length of 7. So now, the total weight of your route inspection is the total weight of the graph plus the arc you go along twice. So it would be the total weight of the graph plus 7.
Gentlemen, if someone were to be looking, let's say, coming into my classroom at this moment in time, what would they see? Would they see a group of year 12?
So now I have
hard
just finished.
Or would
Can
they see
I
some
get on
killers?
with this? Right.
I vibrated.